Hi everybody! This chapter is called Techniques of Integration. But before we talk about what that means, I just want to introduce the indefinite integral. You already know about the definite integral. The definite integral looks like this, and it is a number. So this whole thing actually represents a number. And as you know, the number represents the area under the curve 2x between the x values 1 and 5. Okay, so the indefinite integral still uses the integral sign, but there are no bounds of integration here. So what does this thing actually mean? What does it represent? Well, if this thing is a number, this actually represents a function, x squared plus c. So what this is actually the most general antiderivative of 2x. Let's just remember what that means. So there's lots of different functions whose derivative end up being 2x. X squared minus pi, x squared plus 17. And we would say that 2x is the derivative of each of those. So each of these is called the antiderivative of 2x. And so you'll notice that 2x actually has lots of antiderivatives, actually has an infinite number of antiderivatives. So the most general antiderivative of 2x is x squared plus some constant. And this constant can be anything at all, because when you take the derivative of this, the derivative of a constant is 0, so that's going to produce our 2x. So it's sort of like this most general antiderivative is the family of equations that cover all of these as special cases. We have a nice notation already, actually several nice notations for the derivative. So if this function is our f of x, this function we could denote by f prime, or we could denote by df dx, either one of those. But we don't have a really good way of saying what's the antiderivative of a function. So for example, if 2x, if this function is our g function, is there something that, like some simple way we can notate what the antiderivative of g is? Well, there is now. That's what the indefinite integral is for. So if I write indefinite integral of g of x dx, this is just like writing f prime, sort of. This is just a notation that means the most general antiderivative of g. So you already know a lot of these. So what's the most general antiderivative of x squared? It's going to be 1/3 x cubed plus c. And you can always check your answers here by taking the result of your integration, take the derivative, and see, does it equal your original function? So here, if I take the derivative, the 3 comes down, and I've got 3 divided by 3 is 1, x squared, and then the derivative of a constant is 0, so that just gives me the x squared. So this should be e to the x plus my constant. Let's see, so sine, let's just try this out. Could it be cosine? Let's just test it. If I take the derivative of cosine, that should actually be negative sine, so that doesn't actually work. So if I have a negative cosine here, now let's take the derivative of this. The derivative of cosine is negative sine, and the negative is going to cancel with this negative to give me sine. So this must be the correct one. Some of these might look intimidating, like you're going to have to do something fancy, like secant tangent, like am I going to have to do some kind of like reverse product rule or something? But actually no. Each one of these integrals is just the reverse of one of the basic derivatives that you already know. So you know that the derivative of secant x is secant tangent. So we're going to call these the elementary integrals because they're just the reverse of all of the elementary derivatives that you already know. Let's fill in the rest of the table. Okay, so you'll do these, they'll be great. But if you remember when we did derivatives, there were these shortcuts that let you find the derivative of more complicated functions that you would get when you combine several elementary functions together. So you might be thinking, are there similar shortcuts for finding integrals? And the answer is kind of, but not really. So let's look at an example. Here's the chain rule. What the chain rule has in common with all of the other derivative shortcuts is these shortcuts let you find the derivative of combinations of elementary functions. So in this particular case, is if we compose one elementary function with another. So let's just do a quick example. let's say f of x equals, let's do e to the x, and g of x equals x squared. In that case, f of g of x is e to the x squared. All right, well, so now I've taken two basic functions and I've combined them together. So ordinarily, this might seem complicated, except we have the chain rule. And the chain rule gives us a simple, like step-by-step way of figuring out what's the derivative of the more complicated thing in terms of the derivative of the simpler things. So let's see, derivative of f, well, that's e to the x. So here, derivative of f applied to g is just e to the x squared. And then times g prime is 2x. Cool, so way to go, chain rule. All right, so you might hope that there was something similar that you could do for integrals. In particular, you might hope that the integral of f of g of x equals, and then there would be some simple thing that you could figure out that would go over here. It turns out that there is no simple thing like this. And in fact, the story gets worse. I chose this example on purpose because it illustrates a common but surprisingly true fact. So, same example, we've got f of g of x is e to the x squared. So, if you were wondering what is the integral of e to the x squared, it's not just the case that there isn't a simple way to figure out what the answer is. It's actually the case that this integral can't be represented as a finite equation. There just is no closed form for this integral. That doesn't mean that the answer doesn't exist. There is a function that is the antiderivative of this function. It's just that we don't have a way to describe that function using a finite equation. So you can actually approximate it, and that's what we'll be doing later in the year. I'll show you a way that you can approximate this thing using an infinite polynomial. But this is a situation that happens a lot, actually, when you're trying to find integrals. There's kind of just a very few types of integral that humankind knows how to find closed-form solutions for. And then the rest of them, either it's not known or there just aren't any closed-form solutions. So there actually are integration techniques. They have names like U-Substitution, integration by parts, that kind of thing. But what those integration techniques are is they're actually just the derivative shortcuts backwards. Here's what I mean by backwards. So here's the chain rule. What would happen if we take the integral of both sides of this equation? This is a little bit hand-wavy here, but if you remember, one of the kind of main ideas of the fundamental theorems of calculus were that differentiation and integration are inverse processes, so they undo each other. So if I have the integral of a derivative, those are going to undo each other, and that's just going to give me my original function. And on this side, this doesn't really simplify, so we're just going to leave it as integral f prime g of x times g prime of x dx. Okay, so this is actually kind of a rule. We've got, oh, I forgot my integration of constant. Sorry, my constant of integration. So if I can find an integral that looks like this tells me what it should be equal to. Okay, well, this might seem kind of confusing, not at all obvious. So let's do an example that is hopefully familiar from just a second ago. Let's say I've got the integral of e to the x squared times 2x dx. And I wanted to know, what is this integral? Well, you might think of it this way. You might think, aha, it looks like I've got e to the power of a function. So we'll call that function g. And then here, I'm multiplying it by g prime. So whenever you have an integral where you see some inner function, and then you see that the derivative of that inner function is being multiplied, it kind of fits this form right here. So here, e to the x is my f prime, x squared is my g, and then 2x is my g prime. And so this tells you that the result should just be f of g, or in other words, e to the x squared plus my constant of integration. Okay, so this technique is actually called U-Substitution. And it might not look to you like I did any substituting here. So when you watch other people's videos, they're going to show you a more mechanical technique, and actually I'll show it to you right now. Here's what the technique is. So let's rewrite our original function. Oops, 2x dx. All right, so I'm going to define my inner function. I'm going to say, and I'm going to call it u. There's no reason you should really call it u. You could call it anything, but conventionally we call it u. So I'm going to say u is equal to x squared here. So then I could be writing this, instead of e to the x squared, I could write it as e to the u. Now the problem is, I need to rewrite the rest of this stuff in terms of u also. So we're going to take the derivative of this, so du dx equals 2x. And now I'm going to do something that I told you very strenuously before that you should never do. I'm going to treat this like a fraction, and I'm going to separate it. If you're feeling sort of angry and tricked right now, that's totally a valid feeling. We're going to justify why you can do this once you're a little bit more comfortable with the process. But for the moment, we're going to do the thing I said you should never do, and we're going to treat this like a fraction, and we're going to multiply through by dx. All right, so what does this let us do? Notice here that I've got 2x dx, and I've got 2x dx. So this nicely lets me substitute in du in place of the 2x dx. So that gives me du. Now that I have an integral where I have a function that is only in terms of u, and du is telling me what is the variable that I'm integrating, I can just solve this integral. So I know that the integral of e to the u is e to the u plus my integration constant. And now I can substitute back in what u is equal to. So that's e to the x squared plus c. And like I was saying before, you can always double check that your ideas make sense by taking the derivative of your result, and you should get what you started with. I want to do one more U-substitution example, but first I want to point out a very important thing. So you got to pay close attention to what is your variable of integration here. So that's what the d whatever is. So integral 2x dx, that's just the most general antiderivative of 2x. So I know that should be x squared plus c. And that's because x is my variable of integration, and you know that because it says dx. Okay, so here, x is my variable of integration, but here it's 2k. So the answer here is not k squared plus c, because that would be treating k like it's my variable. Instead, k is just a constant, because I know x is my variable of integration. So instead, we've got 2k, integral 2k dx should just be 2kx plus c. And again, you can double check that. What if you take the derivative of this? That's like this 2k is like a constant, right? So you could say like 5x plus c. The derivative of 5x would just be 5. So the derivative of 2kx is just 2k. So that looks like it's worked. So I just wanted to caution you, because you have to pay close attention to what your variable of integration is. If I said, what's the integral of 2k dk, now k is my variable, so you can write it as k squared plus c. All right, so now that you are duly cautioned, let's do one more example. All right, so here's an integral. This is a case where you might want to use U-substitution, because it's sort of like doing the chain rule backwards. And remember, your first step is always figure out what is the inner function, and then to look for the derivative of the inner function. So it seems like here's my inner function, that's u, and it looks like here I've got u prime. So I think this is going to work out. Let's actually do the mechanical steps. So I'm going to define u to be x squared plus 4. I'll take the derivative, du dx is 2x. And now I'll go ahead and separate these two. So I've got 2x dx. And now I can rewrite this all in terms of u's. Here I've got u to the 99th power, because I have x squared plus 4 was u. And then I've got a 2x and I've got a dx, so I'm going to combine both of those together, and my 2x dx is going to get replaced with du. So now I'll go ahead and evaluate this, and I'll just use the power rule backwards. So this is like 1 over 100, u to the 100 plus c. And again, double check that. You can take the derivative of this. The 100 comes down to cancel, leaving just u to the 99. And now I'll substitute back in for u. So I've got 1 over 100, and then my u function was x to the 4th plus 4. Oops, sorry, x squared plus 4 to the 100th power plus c. And again, I think it's a good idea to double check by taking the derivative. All right, so that seems to have worked. I want to show you now that actually you can use U-substitution even when the derivative here actually isn't present. So consider this variation. The problem's exactly the same, only instead of 2x, I've got 7x. So I can still call this function my u function, but this function isn't exactly u prime anymore, because u prime would be 2x, and instead I've got 7x. But that's not such a big deal. Let me show you two different ways you could think about it. So again, I'm going to define u to be the inner function. I'm going to take the derivative. And the way that we did it before was I solved for du. Well, notice instead of solving for du, I could also solve for dx. So I'll just take this equation and I'll divide both sides by 2x, and that gives me dx equals du divided by 2x. So if I wanted to, I could now substitute this in for the dx, and let's see what happens. I've got 7x times u to the 99 times, and then dx I said was du divided by 2x. Well, look what happens. I've got now, I'm going to move this part over a little bit. So 7x over 2x, u to the 99 du. So the x's now have canceled, and I've got 7 halves u to the 99th du. So this is great. I can solve this just like a normal integral because I know that this 7 halves is just a constant. So this is going to be 7 halves times 1 over 100 u to the 100 plus c. And again, you can double check by imagining taking the derivative. The 100 would come down and cancel this, and we'd still have our 7 halves there. And then lastly, we'd substitute the u back in. So that'll be 7 200ths, because I'm combining those together. And then my u function is x squared plus 4 to the 100th power plus c. Okay, last example, I promise. So this one doesn't obviously have an inner function or an outer function. However, if you see something that looks like it could be factored, it's worth trying to factor it. So it seems like this one is actually going to factor as x plus 1 squared. And actually, I know that because this blob squared is in the denominator, I could rewrite this as x plus 1 to the negative 2. Same thing, right? So now it seems like I do have an inner function and an outer function. So I could define my u function to be x plus 1. Let's see, is the derivative of the inner function present? Well, the derivative of the inner function is just 1, so it seems like it's going to work. So let's try and do it. So du should be 1 times dx. So I can rewrite this as u to the negative 2 du. And if I take the antiderivative, let's see, so that's going to be negative u to the negative 1. It's always worth double checking these things because it's very easy to get confused and do it backwards. It's very easy to accidentally take the derivative here by using the power rule. So here if I take the derivative, the negative 1 comes down to cancel and it becomes a negative 2, and that's really gotten me what I want. Okay, great. So I'll substitute my back in for my u, and that gives me negative 1 over x plus 1 plus c. So again, it's really worked out. Okay, really for real, the last one now. So this is exactly like the last problem. I just put an x in the numerator, and that looks like it's going to really mess up the works here. let's do what we did before. So I'm going to factor the denominator. That gives me x plus 1 squared dx. And I guess I can try and apply U-substitution. So I'll have u equals x plus 1. So that means du dx equals 1, which means du equals dx. And so now I can go ahead and substitute. So here's my x plus 1 is my u function. So I've got u squared down here. Dx is the same as du, so I've got du here. But I still have this pesky x here in the numerator. So I can't take this integral until I figure out how to write x in terms of u. Here's why I say keep the faith. If you're trying to use U-substitution and you're not able to substitute everything, keep working with it until you can. So I'm noticing we've got this equation up here, and an equation just means this side is equal to this side. I want to know what x is in terms of u, so let's figure it out. So I'll just solve for x. Here I'll isolate x by subtracting 1 from both sides, and so now I've got that x should be u minus 1. So that's actually great, because it lets me substitute that in here. Yay! Whoops. All right, so u minus 1 is actually what that's equal to. Okay, well, how has this helped us? Now I've got a fraction that I can split into two parts. This could be the same thing as u over u squared minus 1 over u squared. And so that'll let me split it into two separate integrals. 1 over u, because I'm letting one of these u's divide the other, du, minus integral 1 over u squared du. This one is natural log u, and this one is the same thing as integral u to the negative 2 du. And so here I'll use the power rule backwards. So this is like we had it last time, so it's negative u to the negative 1. Yep, that makes sense. And then there's a constant associated with each of those. So we've got a plus c, and then we've got a different plus c. So I'm just going to combine those together to be a third plus c. All right, so that gives us natural log u plus 1 over u plus c. So I think the moral of keeping the faith is sometimes it's possible if you work enough with your original equations that you can actually substitute all of your things for u, and then you're usually good to go.